Hello everyone, my name is Tarun Rutvik Kandeti and this is my presentation for task 1.2T. Oh, shit. Welcome everyone. Today I'm going to talk about one of the most famous open problems in all of mathematics and computer science, P versus NP. If you heard people say this problem is NP hard and quietly nodded while having no idea what it meant, you're in the right place. By the end of this tutorial, you'll not only understand what P, NP, NP hard, and NP complete actually mean, you will feel it. You'll have the intuition. Let's start from the very beginning because the best way to understand these complexity classes is to first understand why runtime matters at all. Why does algorithm speed matter? Let's start with the question. Why do we care how fast our algorithms are? The answer seems obvious. We want things to run quickly. But the real insight is deeper than that. Look at the three cards on the screen. It's the same algorithm but different input sizes. With 100 items tasks like sorting, routing, searching it finishes it almost instantly. No problem whatsoever. With 10,000 items, it's still manageable, but a few seconds to output. But when we introduce a million items, some algorithms grind it to a halt or take days at a time, or never finish in our lifetimes, honestly. The key takeaway from this is that faster hardware does not save you from poorly scaling algorithm. You can double your processor speed, you can run it on a supercomputer, but if your algorithm's runtime grows exponentially like 2 to the power n sort, then throwing hardware at it barely buys anything. Runtime growth, the mathematical shape of how your algorithm scales, is what matters. And that's what complexity theory is all about. So before we talk about P versus NP, let's make sure we understand the tool we use to measure. What is time complexity? Time complexity is a formal way of answering, if I give this algorithm a bigger input, how much work does uh, does it do? Crucially, it does not measure seconds. If I run the same algorithm on your laptop versus a server farm, the seconds are different, but the growth pattern, that's completely the same. That's a universal truth we're after. So when we say an algorithm has linear time complexity big of n, we mean double the input, roughly double the work. So quadratic big of n square means double the input and quadruple the work. Similarly, exponentially, if big of 2 of the power n means add just one item to the input and the work doubles entirely. We express all of this using Big O notion, which we'll see on the next slide. Think of Big O as a language for describing the shape of growth. Here are the major complexity classes you'll encounter, ordered from fastest to the slowest. O of 1, constant time. Doesn't matter how big the input is, it takes the same amount of work assessing index 5 in an array. Always one operation, it is completely perfect. O of log n, logarithmic. Binary search is the classic example. Every step cuts the problem in half, even on billion items. You're done in about 30 steps. Big O n, linear. You touch each element once, perfectly proportional, and totally fine. O of n log n, linear rhythmic. Most efficient sorting algorithm like merge, sort, heap sort. And it's still very practical. O of n square, quadratic. Nested loops over the data, bubble sort. Starts to hurt at large n, but still manageable. Big O exponential. This is where things start to fall apart. Adding a single item to the input can double runtime. Big O n factorial. The most catastrophic growth. At n is 20, we're looking at 2.4 quintillion operations. No computer on earth will ever finish this large of large inputs. Notice that dividing line on the screen. Everything above is polynomial, everything below is exponential. That boundary is the heart of P versus NP. Let me make this boundary even more visceral with real numbers. Polynomial versus exponential. The O moment. Take n is equal to 50, 50 items. Not a million, not a billion, just 50. If your algorithm is quadratic, n squared, that's 2500 operations done in a blink of an eye. If your algorithm is exponential, 2 to the power of n, that's 1 quadrillion, 125 trillion operations. That's more operations than there are grains of sand on Earth for 50 items. This is not a hardware problem, this is a mathematical wall. No chip, no cluster, no quantum computer makes a dent in this gap. This is why computer scientists had to invent a formal way to classify problems, to separate the ones we can solve from the ones that are, for all practical purposes, unsolvable. That's exactly what P versus NP is about. Real world problems that hit this wall. This exponential growth isn't just a textbook curiosity, it appears in some of the most important real world problems. For example, the traveling salesman problem. Uh, it's to find the shortest route that visits every city exactly once and returns home. Simple to state. With 20 cities, there are over 60 quadrillion possible routes. Brute force is not an option, it's completely hopeless. Another one is chess and go. Even with the best hardware, optimal play requires looking ahead through a trees of moves that grows exponentially with depth. Modern chess engines use brilliant heuristics, not brute force. Then we have the job scheduling, assigning tasks to workers with constraints so all deadlines are met. Sounds like a management spreadsheet problem. At scale, it explodes into the exponential. Even in biology, protein folding, that's how a chain of amino acids fold into its 3D structure, determines its function. The configuration space is exponential. This matters enormously for drug discovery. These problems are not logically impossible. You could, in principle, enumerate all routes, all moves, all schedules. They're computationally impossible. Too much work for any machine in any reasonable time. That distinction is critical. So, what is P? Now we're ready to define P. Formally, P is a class of decision problems that can be solved by a deterministic algorithm in polynomial time. Decision problems means the answer is yes or no. Polynomial time means big of n to the power of k for some fixed k. The intuition here is that P is efficiently solvable. These are tra- tractable problems, the ones computers are great at. Look at examples sorting O of n log n, finding the shortest path with Dijkstra's algorithm, also polynomial. Graph traversal, matrix multiplication, finding the greatest common divisor, all polynomial, all in P. P is our comfort zone as engineers. It's all about the shape of growth, not raw speed. If a problem is in P, we can build a system around it. We can scale it. If a problem is not in P, that's where things get interesting. P problems are solvable. But what about problems where we can't find a solution efficiently, but we can check one? That's NP. So, what is NP basically? NP stands for non-deterministic polynomial time, but the name is a bit misleading. The cleanest intuition is that NP is the class of problems where if someone hands you a solution, you can check whether it's correct in polynomial time. Not necessarily find it, but just check it. Sudoku is a perfect example for this. Look at the grid on the screen. If I hand you a completed Sudoku and ask, is this valid? You just scan each row, column, and the box for duplicates. Easy, it's polynomial. But if I hand you an empty Sudoku and say, find the solution, that's a bit of a difficult or a different problem. There is no known polynomial algorithm for that. Also, note that every problem in P is automatically in NP. If you can solve something efficiently, you can certainly verify a solution efficiently. So P is a subset of NP. Solving versus verifying. The core insight of this is this slide is the single most important conceptual moment of this tutorial. Everything else builds on this asymmetry. Finding a solution to Sudoku is trying all possible combinations until something works and is, as far as we know, exponentially hard. No efficient algorithm exists. Checking a solution to Sudoku, that is, scanning for rule violations, is trivially easy. A few nested loops, polynomials, and done. These two tasks, solving and verifying, feel like they should be similar, but they might be fundamentally different in difficulty. That gap is P versus NP. Think of it this way: writing a great novel is hard. Reading one and saying, yes, this is brilliant, is easier. Finding the right key in a locked room might take all night. Checking that key opens the lock takes literally a second. Cracking a safe is hard. Looking at the combination and verifying it if it opens the safe is easy and instant. NP problems have this property: hard to find and easy to check. The big question: does P equal to NP? And now we arrive at the question that has stumped every mathematician and computer scientist for over 50 years. If checking a solution is easy, does that mean finding one must also be easy? Does P equal NP? This is not a rhetorical question. Nobody knows the answer. It has been open since 1971. It is one of the Clay Mathematics Institute 7 million Millennium Prize problems. There is there is a $1 reward for a $1 million. Sorry, there's a $1 million reward for a valid proof either way. Most experts believe P does not equal to NP, that there is a genuine fundamental gap between finding and verifying it. But most experts believe is not a proof. If someone proved P is equal to NP tomorrow, it would immediately break most of the encryption protecting the internet. It would revolutionize medicine, logistics, AI, and practically everything. The implications are almost impossible to overstate. Conversely, proving P is not equal to NP would confirm what most already suspect and give us certainty about the limits of what computers can ever efficiently solve. What is NP hard? Now, we need to distinguish two related but distinct concepts: NP hard and NP complete. Let's do NP hard first. A problem is NP hard if it is at least as hard as the hardest problem in NP. Formally, this is defined through a concept called polynomial reduction. We say X is NP hard if every NP problem can be transformed into X in polynomial time. The idea, if you could solve X efficiently, you could use that to solve every NP problem efficiently. Here's the critical subtlety about this where many people get confused. NP hard problems do not have to be in NP. Remember, NP requires that solutions can be verified in polynomial time. Some NP hard problems don't even have solutions. You can check efficiently. The classic example is the halting problem. Given a program, will it ever stop? That's NP hard. But you can't even verify a solution efficiently. That it's not NP at all. So NP hard is a lower bound on difficulty. It means at least as hard as NP. It says nothing about whether the problem is in NP. So what happens when a problem is both NP hard and inside NP? These are the NP complete problems. What is NP complete? NP complete is the intersection of NP and NP hard. A problem is NP complete if it satisfies exactly two conditions. First, it's in NP. That means a proposed solution can be verified in polynomial time. Second, it's NP hard. That means every other NP problem can be reduced to it polynomially. NP complete problems are the hardest problems inside NP. They're the frontier, the cliff edge. The first problem ever proven NP complete was the Boolean satisfiability problem, SAT, proven by Stephen Cook in 1971. His proof showed that SAT is the canonical hard case for all of NP. Since then, thousands of problems have been proven NP complete by reduction from SAT. Knapsack, can we pack items to exactly hit a weight limit and be complete? The graph coloring, can we color this graph with K colors with no 2 point adjacent nodes sharing a color and be complete? The decision version of TSP, is there a tour shorter than some number K? That's NP complete as well. The powerful consequence, if any NP complete problem we've solved in polynomial time, it would immediately prove P is equal to NP, and all NP problems would be solvable efficiently. The complexity landscape, nested circles diagrams. Here's the visual that ties everything together. The innermost region in green is P. Every problem here can be solved efficiently, sorting, routing, searching, and all that. Around it in the amber is NP. Everything in P is also in NP, which is why P sits inside NP. The NP region contains problems where solutions are easy to verify. On the right side of NP, in purple, you see NP complete. These are the hardest problems inside NP. They're still in NP, solutions can be verified, but they're also NP hard, meaning everything else in NP reduces to them. The outermost oval in red is NP hard. Some It extends beyond NP because some NP hard problems, like the halting problem, aren't even in NP at all. They're harder than anything NP contains. Remember, this diagram assumes P is not equal to NP. As most experts believe, if P is equal to NP, where true P and NP would be in the same circle, NP complete would collapse into P. And cryptography, as we know, it would break. Why this matters in the real world? So, why does any of this matter outside of theory? The answer is cryptography. The security of RSA encryption, which protects your browser, your banking, your messages, relies on integer factorization being computationally hard. If P is equal to NP were proven wrong, a polynomial algorithm for factoring would likely follow, and most public key cryptography would break instantly. The entire internet would need to be resecured overnight. Google Maps. Finding the shortest path between 2 points, that's Dijkstra's algorithm in P. It's fastly solved. Another example, finding the optimal multi-stop delivery route. That's TSP NP hard. Google uses sophisticated approximation algorithms to give you a good route. Not necessarily the perfect one, but a good one. Logistics and supply chain. Amazon's delivery optimization, airline scheduling, hospitality staffing, and all NP hard at scale. The savings from even 1% improvement in route efficiency are worth billions. And the final example, artificial intelligence. Optimal planning, game playing at depth, and certain neural architecture searches touch NP hard territory. Modern AI breakthroughs often come from finding clever structures that make hard problems tractable. How we deal with NP hard problems. Knowing a problem is NP hard doesn't mean you give up. It means you change your strategy. Approximation algorithms give you a solution guaranteed to be within some factor of optimal. For TSP, the Christophorides algorithm gives a solution at most 1.5 times worse than optimal. You don't get perfection, but you get a provable bound. That's oftentimes enough. Randomized algorithms use chance to explore the search space. They often find excellent solutions very quickly, even without guarantees. Heuristics, genetic algorithms, stimulated annealing, ant colony optimization, mimic processing in nature to search huge spaces efficiently. No proof of quality, but in practice, often remarkable results. Special structure. Many real world instances of NP hard problems have hidden structure. A graph that looks general might actually be sparse or planar or tree like. Exploiting that structure can make the problem tractable. Fixed parameter tractable. Algorithms contain the exponential blowup in a small parameter. If the number of colors is k is equal to 3 or the tree depth is bounded, algorithms can be efficient even if n is huge. And quantum computing, while it doesn't break NP hard in general, offers quadratic speedups via Grover's algorithm and opens new avenues we're still exploring. This is a quick reference table. Let's put it in all in one place. P can be solved efficiently, can be verified efficiently. Examples including sorting, Dijkstra's algorithm, and BFS. NP solutions are unknown. Verified? Yes, always. Polynomial, and the examples may be Sudoku, graph problems, and others. NP complete solutions. They are unknown as well. And that means no polynomial algorithm found. Verified? Yes, it is a polynomial. Examples maybe SAT, TSP, decision, click, knapsack. Yeah. NP-hard solutions are not polynomial, and verification is not necessarily possible. TSP optimization, the halting problem, they're two of its examples. Each class is a strict subset of the NP, assuming P is not equal to NP. To conclude, Let's land this plane properly. Complexity theory is the branch of computer science that asks what can we efficiently compute? Not can it be computed in a theory, but can it be done in time we can actually use? P problems are our workhorses. Fast to solve, fast to verify, sorting, routing, searching, etc. are the backbone of everyday computing. NP problems expose a profound asymmetry. Checking an answer can be easy even when finding it might not be. NP hard problems are, at minimum, as hard as the hardest NP problems. Some go beyond into undisability into problems no computer can ever fully solve. NP complete sits at the intersection, the hardest problems inside the NP. Solve one efficiently and you solve them all. Prove P is equal to NP and win $1 million. And when NP is NP hard, we don't give up. We approximate, we randomize, we exploit its structure, and we use heuristics. The limits of computation are not a dead end, they're a design constraint. Knowing them is what separates a thoughtful engineer from one who just tries to brute force everything. Thank you so much for watching, and I hope this helps you at least a little bit. Thank you so much.